So, I don't know where we left off. I believe talked about means, but we didn't talk about the variance. So, a couple things off the top today before I forget. And this is why I try not to be an admin professor and write things down so I don't forget anything. Okay. So, I guess stupidly thought that the section numbering has something to do with time. So I switched the two sections up because the larger number is actually you guys. So I think the exam date that I showed you for the final last class is actually going to be different. So I've got the slides and the syllabus now updated so that it should have the correct day and time. Once again, I apologize for that. I just thought the larger number meant it was probably, that's how it is from other sections, that it's the section that's later in the day. But in that case, or in this case, it's not. So I'll have to get used to that, and I'll probably make call you guys the wrong section at some point throughout the semester. But this is not a correct now on Canvas. Will be the correct final exam time for this section. Yeah.
So, exam time is
correct. And so I should be updating the slides and the syllabus that are now on Canvas because we're section 37337. My other section is like 7295. It's a smaller number. I thought that the section numbering was based off of time of the day. Apparently it's not. Right? For every section I've had, so like for every semester I've had so far, it's always been like that. But this, I guess, is I think this class got scheduled late. It was like an additional section that I agreed to teach. So I think because it got scheduled later, that's why the numbering is a little bit off. So I apologize for that. But of course, the materials on Canvas should now be updated to have the correct day and time. Okay. The second thing is, I think, something that some people are having an issue with. So once you can get, a lot of us, I think, in class got state of working okay. I don't know what is causing this necessarily, like what type of operating system. Some of them it does, you don't have to do this, some of them you do. But once you kind of get that Citrix downloaded, even if you open it, you still might be having some error issues, like it won't open up the file. Like I think someone was talking from another section that was trying to use R to open up state of program. It wasn't using the actual state of program. So if you're having issues with it, even though you think you downloaded Citrix, if you go to IU Anywhere, if you can get to this point, right, where you can see your apps and everything. So let me see. Okay, well, it's not going to let me do it again, but you'll like detect Citrix and then it should send you right here. If you go to settings, account settings, and this is in the initial state of help video I had on the YouTube page. I actually had this step in there as well. So I renamed it alternative state of help or something, state of help alternative or something like that. Because for some of you, for whatever reason, you have to go to the settings and hit activate Citrix or workspace app. Right? And then it'll kind of have this additional thing, you'll run it, and then you should be able to go back and open up Stata just fine. Okay? So try it. If you're having some issues, a couple of you reached out to me, I said, mentioned in class. If you're still having issues with it, I will kind of expect that you're able to work along with me starting next week. Be ideal if you can work along with me today. So how many of you have been able to get it Stata opened on your computer? Okay, good. How many have not? Couple of you? Okay. So if you're still having issues with it, try this, right? Try activating it. Are you able to see, get to this point, this screen, those of you who have it?
Yeah.
Okay, yeah, I think it's probably going to be, yeah.
I actually wouldn't maybe run this class. I was in here last week.
Okay.
So what was the thing you searched?
Yeah, so talk to me after class. There's a couple different steps, but there's a video on YouTube. There's a YouTube playlist, search Professor Lannis. I'll be the one that pops up. You'll see our section as kind of a walkthrough. If you want to watch it now and mute it and try to get through the steps. But for those of you who are here on Tuesday and we're having issues, often this route will kind of solve that. Okay. Any other questions from me before we kind of jump into material here today? We'll really kind of hit the ground running, diving into material today. Also, it looks like there's quite a few more of you here today, so that's good. I know. I think this section was the one, I was only supposed to teach one section of this and there was like 35 of you on the wait list. Did any of you, was it spring? True, yeah. And then, so then I agreed about, I don't know, was 2-3 weeks before the semester started to open another section. And so now I think you are the result of that. So I know that's probably also why we're all the way to hell, all the way over here, right? But some of you that works out. So let's go to the slides. We talked about all this. Let's go here. So what we didn't talk about was the variance. So we talked about the mean, the median, the mode. The mean is often what we call the first moment of the data, right? The second moment of the data, and you might not have heard this terminology before, and I honestly won't use it very often, but it's going to be the variance, right? So the variance is something, we look at the average, we look at the mean. Well, you could have two groups have the very, very similar mean. So I might have two classes, and they might have the exact same average grade, but one of them, every single person got an 80, and the other one, some people got 60, some people got 95s. There's a much wider distribution. There's a lot more variation in that second class. We can measure that variation calculating the variance, right? So how do we do that? We go through, we kind of talked about this last class, population variance. So we're using sigma, right? This is also sigma, it's just lowercase sigma, to represent the variance. Sigma squared is going to be our variance. The summation sign says, okay, go through every single observation in your data set, take the very first observation's value for this variable y you're interested in finding the variance of, subtract the mean, right? So in order to calculate the variance, you'll have to have already calculated the mean, right? Once you do that, take that, what we call deviation from the mean, right? So it's going to be that observation's difference from the mean or deviation from the mean. We're then going to square that and then do that for every single observation, add them all up, and then kind of like with the mean or the average, we then divide by the total number of observations in our population. Okay? Questions on that idea before we keep moving? This is kind of hopefully sounding somewhat familiar from 370 or whatever your 370 equivalent was. One thing I like to say with the variances, so you're essentially getting like the average variation from the mean. It's another way of thinking about it. With a caveat of, it's not just the average deviation, we're squaring that deviation. So what does that do? If I take 1 and I square it, that would just be 1. So if I'm 1 away from the mean, it would add 1 to that numerator. If I'm 2 away from the mean, I square it, I would have 4. So then I add 4. 3 away, I get 9, right? So when I square things, the further I get from that mean, it's going to be adding even larger values to that numerator. So what the variance does is it becomes larger and larger, or think about it this way, it over penalizes really large deviations from the mean, right? Because the further I get from that mean, once I square it, it becomes even larger, right? That relationship is not just 1 to 1. Like I said, 1 becomes 1, 2 becomes 4, but then 3 becomes 9, right? So it adds a whole bunch as I start to get these really extreme deviations from the mean, okay? We can do this for a discrete random variable as well. It looks pretty similar. We go through every observation, we take the value that we see, subtract the mean of that discrete random variable, square it. The only difference is we then multiply by the probability we saw that value for y. And I talked about last class when we were calculating the mean for this discrete random variable. Really, that dividing by the population size is kind of floating behind the scenes there, because to get a probability, if 10 out of 40 of my students get a B in the class, how do I come up with that probability? 10 over 40, right? I'm actually already dividing by that total number of students in my class, or that n. So it's kind of floating behind the scenes, even for a discrete random variable. Okay. We can scale the variance. It becomes useful when we start to do things later, like standardized variables, which I think we'll get through today. Instead of using the variance, we calculate the variance, but we might want to scale it to get the standard deviation, right? And this becomes more useful in some of the stuff we'll do later on in the semester. So sigma, just not sigma squared, but sigma is going to be kind of just the square root of our variance. Oops, which I didn't put it here, but if I take the square root of something squared, that just becomes itself, right? That cancels out. So sigma is going to be our standard deviation. It's just scaling our variance by taking the square root of it, okay? And if we have the standard deviation, how can I get the variance? Just square it. Yep, so we can go back and forth pretty easily between those two statistics. Okay. How would I look at like a discrete random variable like this, just to kind of do a little bit of review and calculate the mean and the variance, okay? So a lot of the times what I'll do is I'll leave slides blank if I'm going to do some work on this dot cannon, right? So I mentioned, I hit record, right? Okay, yeah. So you'll see during this time, like on the video, you won't see anything I do with the dot cannon, right? So I want to show you this. There we go. All right. You see this okay? No, we'll see once I start writing. So I think you have those slides pulled up in front of you. You have all these different values for y, and you have the probability associated with each one of them. Right? So the way that we'll find kind of the mean of this discrete random variable is take each value we could see at yb, multiply it by the probability we see yb that value. So in the context of this example, the very first outcome we could have seen for this y variable was 0. The probability associated with seeing 0 was 0. So that one's really not that interesting, right? We in fact could have technically skipped it, although just to be good practice, we really do need to, we are truly taking every outcome. If it doesn't have a probability, right, well then it really won't impact the mean. But let's say 0 did have a probability that was positive, like 0.01, we would still need to, we would want to kind of write this out like this. The next possible value for y was 1. The probability that we saw y equal to 1 right next to it was 0.06. We then would add to that the next possible value for y, which was 2, times the probability we saw y be equal to 2. The slide I had that was 0.03. You then essentially just continue to do that all the way until we get to the very last possible value for y, which was 12. It had a probability of 0, so really we kind of didn't have to factor that one either, because anytime you multiply something by 0, it's 0. Right? So this would be the thorough process of how we would calculate the mean. Go through every single possible value for y, multiply it by the probability it occurs, then add them all up. Okay? Excuse me. Any questions on that? Okay. How would I then find the variance, right? So let me see, I'm gonna cheat because I forget. Oh, I don't remember the number that it is. I can cheat though using Excel real quick. Oops. So you guys can't see what I'm doing here, but it's, no, I guess you'll have to, I'll show you once we go back, so you'll have to, oops, trust me right now. So if I were to go through I can probably show this to you so you can see what I'm doing. So I just copy and pasted those values from the PowerPoints. So what we were doing, we were going through every single possible y value, multiplying it by the probability that y occurred. So left off the headings, but this was y. This is the probability y was equal to that specific y value. Make this so we can actually read it, right? So what I could do, I could write this all in one big equation, or if I'm in Excel, this is really what I'm doing for each observation. I was saying, okay, look, take this y value, multiply by probability that y takes on that value. I'm going to do that for every single one of these possible y values, and then going to add them all up. So 5.12 is our mean. Right? You can do it by hand, but Excel makes this pretty handy as well. Hopefully, whoever you had for 370 or the equivalent showed you how to use Excel. I partner everything I do, showing how students how to do it in Excel. If you didn't, I won't use Excel a ton. We're actually going to be using Stata a lot more, but just as kind of a quick way to show you, it makes it pretty handy to do calculations instead of doing by hand. So we've got 5.12. How would I then find my variance? Well, remember, that was going to be, I'm going to go through and add up every single y value's deviation from the mean squared. But it's a discrete random variable, so I still need to then multiply it by the probability I saw that deviation from the mean. Right? So we would go through the very first value, which was 0. Subtract that mean, which we just calculated was 5.12. Square that value. Multiply that by the probability we saw 0. So this one's not that interesting, right? Because 0 times anything is just 0. We would then add in the next possible value for y, which was 1. Subtract that mean of 5.12. Square it. Multiply it by the probability we saw y equal 1. right, which was 0.06. Then we would do what's the next possible value for y? 2. What was its deviation from the mean? Square it. Probability we saw it take on the value of 2 was 0.03. We kind of continue this all the way to the very last one. Right? So this would be the process that you use to calculate means and variances for these discrete random variables. I think I'll kind of pull open some practice problems that we have just to kind of get an idea how we kind of solve this for that for kind of moving forward exams down the road. Okay. All right. Or the quizzes as well. So what I want to do now, I'll go back to here and I will show you, since I already had it set up in Excel, I might as well. I'm going to show you, you can do this pretty easy in Excel too. How could I find my variance? Well, really what I wanted to do was I wanted to add up. Let's type it out. So I'm going to go find the Greek letters, right? The deviation from the mean squared times the probability y was taking on that specific value. Okay? So again, you guys probably can't read this too well. So there we go. So I'm going to go through, I'm going to take every single y value. I'm going to subtract the mean. I shouldn't have been lazy with this. I should have started with my parentheses because I'm then going to take that. I'm going to square it. Okay? I'm then going to multiply that by the probability I saw y be equal to that value of 0. Now, trick in Excel, if you're not familiar with it, I don't ever want this cell reference to change. Oops, I put that in the wrong spot. So I'm going to use dollar signs to freeze it. Now, when I copy this down, it's taking this y value, subtracting the mean, squaring it, multiplying it by that probability. I have one more step, which is I did this for every single observation. I'm now going to add them all up. So here, I get that the variance is, just coincidentally tends to be close to the mean, which is what, 5.4, right? And I could do that all by hand as well, in the way we wrote it out up here. I'm just doing an Excel here just to kind of give you some values that maybe if you do want to do it by hand, you can kind of check yourself. Now, if I wanted the standard deviation, what's the only thing I need to do? Square root that. Yeah, so I can do that pretty easily on a calculator or in Excel as well, okay? Any questions on anything there before we keep moving? Okay. All right, so back to the slides here. I don't know why this computer is so slow. There we go. That's the easy one. So we went through that. I'll go through these quickly. We want to do these calculations. I'm going to end up showing you how we get these statistics from data later today. But we've got the first moment, mean, second moment, variance. We can kind of continue. Third moment is going to be what we call skewness. So when we're thinking about skewness, it's essentially going to be a very similar kind of process, but a little bit different. So we would take kind of this deviation from the mean, but to the third power, instead of dividing by n, we divide by kind of what this skewness would be. So we're not going to really ever calculate this by hand. We're going to have Stata do this for us. But what it picks up is that not every distribution, right, is going to look exactly the same. So some will be symmetric, some will be a little bit different. So I always use the example of, if you think about like income tends to have a really long right tail. Because like the majority of us make between 0 and I don't know $100,000. That's where the vast 90 probably +% of people are in that range. But then you've got like Elon Musk, right? So that right tail tends to be really, really far out. But right, the left side, it stops at 0. Right? So we kind of, anytime you have like it's not perfect, but you can think of it this way. Anytime you have this kind of long right tail, we kind of think of that as a positive or right skewed. Right? We've got extremely large values or extremely large outliers for those right skewed distributions. A symmetrical distribution, I think I mentioned this last class, like the normal distribution, the mean actually ends up being the same as the median and the mode. And we have what, if it's perfectly symmetrical or normal, it's symmetrical, so there's exactly the same shape, right, on either side of that mean. You could fold it on top of itself and it's exactly the same. Left skewed data, it's a good example of left skewed data where we don't see, you can talk about something like, this is kind of morbid, but flu, and then I did bring up the flu vaccine example in this class, or was that might be at 251. So I always use this example for economics, like the flu vaccine actually might have a negative correlation with dying from the flu. Why? You guys getting the flu vaccine? How many of you got the flu vaccine? Couple. Why don't you get the flu vaccine? Because if you get the flu, you're probably not going to die. If you're 85, if you don't get a flu vaccine, it might be the last flu you ever get, right? So if you look at like deaths from the flu, you're always going to have way more people on that right-hand side and not near as many. In fact, that one, you'd have a little bump because when you're really young, that's probably a bad example because there's, you're at risk when you're really young to die from the flu as well. But if we're thinking about maybe people aged from 5 to beyond, you'd have nice less skewed data, right? You're not going to have many people dying on, very low number of young people dying from the flu. Most of those deaths are going to come from older age. Okay. All right, and just a foreshadowing. Once we get to regression, we'll actually have ways we can tease out and say, okay, yeah, we see this negative relationship with the flu vaccine and dying from the flu, but we know the causal relationship is probably not that. And we can hold things constant and actually see what the effect of the flu vaccine actually would be. And spoiler alert, ends up being positive, right? Once we can control for those factors. I won't waste too much time on this either. Kurtosis, really, it's, skewness is going to be kind of whether or not we have that long left or right tail, extremely low values, extremely high values. But kurtosis is going to measure kind of like how fat our tails are. So you could see, try to draw, oh, it's cutting out. Where's the screen button? Is it not all the way down? Nope, that's not it. There we go. All right, so you'll kind of notice here, even all of these distributions are symmetric. Like if I fold them on top of themselves, they're exactly the same. This one down here, that's like a lot flatter, we would say has negative kurtosis, or kind of that has a larger, it has fatter tails, right? So we think about the y-axis here representing like the probability I see this variable take on these certain values. It's much more likely when I have a larger kurtosis, I see those fatter tails, it's much more likely I see values that are further from that mean. It's a little bit different than the variance because it's measuring not just the kind of average variation from that mean, but like how fat these tails are, right? How high these probabilities are. And then as I get kind of like a more peaked distribution, I get these positive kurtosis or much smaller values telling me that more of the, even though the vast majority of the data is in the middle, I've got really kind of small tails there on the left and the right. Okay. So we can get all of these from Stata, and we'll take a look at that in just a second. But before we do, I want to go through one more kind of thing, and then we can look at all of it in Stata and kind of, don't have to kind of keep jumping back and forth. Okay. So we can kind of think about variables having their own distribution, right? So I've used like income, flu data. We could look at any variable and kind of figure out what the distribution of the data looks like, right? We can also have joint distributions. So I think here I do class size and then like the math scores. So this is maybe I'm looking at like high school or elementary level, like standardized math tests. So I'm looking at what the size of the class is, right? We might think that, if the smaller the class size, the teacher can devote more time to each student, and maybe we see higher math scores. So one measure of this correlation, like is class size correlated with, that's often how we talk about it, is it correlated with higher math scores here? One of the measures that we'll use, which is not the correlation or correlation coefficient, we have to first start out in order to calculate that, we're going to use what we call the covariance. Okay? So the covariance, once again, we're trying to kind of get used to some of these symbols. I'm going to sigma, and then you kind of put what two variables you want that covariance between. So you'll go to the first variable. So you might have, this data where you've got every different class and how many students were in it, and then what the average score in that class was. So you go to that very first school and say, okay, what was that school's deviation from, what was that, class size? So how many students do they have in their class? Subtract what the average school had, or the average, classroom number of students was. You'll then take that deviation for that class size and multiply it by that room's deviation from the average math score. Once you have both those deviations, you multiply them by each other. You would do that for every single observation in your data set, right? You then add them all up, and that's your covariance, right? Now you can think about what the covariance is going to tell us, right? First of all, the units are always going to be kind of weird because you're multiplying two variables. So like here I'd have what, student point, like number of students times the points on this exam. So the units like student point, the units make it weird. So now I can't really compare covariances across different types of relationships, right? Because student points wouldn't be the same as if I wanted the correlation between, oh, I don't know, age and the number of hours sleeping, right? There I would have year hours. And so at my units, I can't compare covariances because they're going to be different for every relationship. And I think about the covariance, like kind of the different ranges it could be in. Every single time I go through an observation, let's say they have below the average class size and below the average math score. So when I have a negative times negative, I get a positive. Because that observation would be evidence that when class size is low, so are math scores, right? So it tends to be on the same side of the mean. Just as if I had an observation where, let's say instead, the class size was below the average, but the math score was above, negative times a positive is a negative. Well, yeah, because that is one observation that's evidence of a negative relationship. Class size was smaller, math scores tended to be higher. Right? And now, obviously, one observation is going to tell me the relationship. I have to then add up and say, okay, what is, after I'm adding all these up, does it look like I have a positive or negative relationship across every observation in my data set? Okay. So the range we can see it be could be negative, could be positive. Positive would tell us that these kind of two variables tend to be on the same side of the mean, on average, across every observation in our data set. Negative, they tend to be on opposite sides of the mean, across every observation in our data set. Now, I mentioned the units kind of make it hard to compare and contrast different types of relationships. For example, I know that the relationship between hours studied and test performance is probably stronger than, oh, I don't know, the amount of income and, I don't know, we'll say smoking behaviors. Smoking kind of happens across all income brackets, so it's not really that strong of a correlation, right? But there's a pretty strong positive correlation between hours you study and your test performance. So we scale this covariance to get a correlation coefficient so we can compare these different types of relationships, right? These different correlations. So all we do is we take the covariance and divide it by the variation that exists in each one of those variables, right? So it's not like perfect math, but I'm not going to walk through the proof and everything, but you can kind of imagine why. So for instance, if I have student points, first of all, if I divide by then each one of those variables, all my units cancel. So I get like this nice unitless measure. Also, you can kind of picture it like when I take the standard deviation, like I'm taking the square root of adding up all these square deviations. Then the deviations also show up in the covariance. So you can kind of imagine, and like I said, the math is a little more complicated, but by dividing by these standard deviations, we get it so that we can scale this to be either a perfect negative relationship, -1, perfect positive relationship, a +1, or typically we're going to see something within that range. Is that any questions on that? I know I'm kind of black boxing a little bit, but really we're not going to be calculating these a lot by hand. We're going to have you Stata do this for us, okay? So I think this is what I love here. Go through. Well, I'll show you this before we jump over to Stata. We can also do things like a scatter plot. Yeah.
So most of the functions, if not all, that like Excel can do, just reading, I think we all do this in the past class.
Yeah.
Calculating covariance, correlation coefficient. Stata can do the same thing, right? We
Yeah.
can just like plug it in.
Yeah, I'll show you in just a second. Yep. And in fact, yeah. And I'll show you some other stuff in there as well. So the other thing I do want to mention before we jump to there though, is we have these correlation coefficients. It's going to be kind of similar when we're talking about linear regression. We think about like, here's our data. We graph every single point, right? So like class size and math score, I kind of kept the same example. I can kind of think about drawing a line kind of through that data that best fits it. And that would tell me like what the relationship looks like between class size and math scores. So we can create these scatter plots as well in Excel, in Stata. So let's take a look at how we do some of this. So let me see. So I think I already had this pulled open. So I drag and drop an additional file, which was a review of statistics, this do file here. I also believe this was already up there with that election data. So I think that's the one that I'm going to use. So we're going to walk through Stata again. Some of you weren't here Tuesday. This might be helpful if you've got it pulled up. So I think before, yeah, we downloaded this state cigarette tax variable. So I'll kind of show you why having this global is helpful, because in the original file I didn't. Excuse me. So I know that I have this defined global. If I try to run this original one, it's trying to pull stuff, gives me this error. It's trying to pull stuff from my personal computer. Well, it can't do that, right? So instead, if I just to kind of show you this, add this global that instead is using my OneDrive, right? That iDrive, and it's pulling from the correct folder, right? I can actually get rid of all of this. I know that the name of the file is the same because I just copied it over from my OneDrive from my computer. I'm going to use that $, and then kind of my brackets, put that word path because I've defined that. Now when I run this, oh, why isn't it like that? Because that's going the wrong way. Sorry. So here. Oh, why isn't it like that? What did I have wrong here? My iDrive, I'm in the right folder. Well, maybe I've got the wrong file path. Let's check this out. We can always use the interface. Maybe it pulls it up for me. Here we go. I must have the path named wrong, so we'll see what the actual name should be. Might have changed the name of one of these folders. So it's in here. Oh, because it's not in that folder. It's in this folder, isn't it? Yep. So I can still show it to you now that I know. So here was the correct one. So I'll copy that. It was not in week 2, it was in week 1. So I made an error as to where the file was, but if I did have the correct folder, I set that global, use that path. Oh, what is it?
It's because the dash is going the wrong way.
Hold on. I changed that, didn't I?
Yeah.
There we go. Oh, and I accidentally deleted my thing. There we go. Now that I have the correct folder, now I can use that global path, or I can, like I said, I can always just open it up using that interface manually as well. But this just allows me to kind of bounce back and forth between my personal computer and one. So I've got this cigarette tax data. We'll eventually look at some other stuff. Here, change this as well. No, I shouldn't use this. Oops. I actually don't use this there. So I'll mention this in a second. So I've got this data downloaded. I can go to my browser, kind of see it. Okay. So just some kind of basic commands that we can use. Try to get this all to be on the screen. There we go. And also, if I forget to do this, always someone remind me. So I can see this. But I know it's a little bit harder for you guys to see it unless I zoom in. So I can rename variables. This becomes kind of useful once you start working with data sets, just because sometimes you'll download the original data and they'll have these really goofy names, right? So anytime you want to rename a variable, like for instance, the state variable. So if we were to look at the data, my state kind of variable, or the location description and location, the abbreviation, those are just kind of long names. And to me, it just makes more sense to call it like, here's the state, here's the state name. So all I do with the rename command is I first put the original name of the variable and then what I want the variable to be called. So now when I run this code and I go back to the data, now this state abbreviation variable is just called state, right? And I can do the exact same thing for the other variable, location description, well, DESC. I rename that. Now it's a little bit easier to look at. Right? So this is just I'm just kind of introducing you to some commands you can use to make life a little bit easier. Okay? Any questions up to this point? Yeah.
How do you open this CSV file? Because I could open the other ones, but
Yeah. So if you go, are you trying to do it from the interface like this? Go to File.
yeah.
Yeah. So if we go to Import, make sure you're not selecting Excel spreadsheet. All right. So CSVs and Excel spreadsheets are a slightly different format, and so the way that it imports it, the way that the program recognizes it, is going to be a little bit different. So I will try to use. I mean, this is like early on. We'll be using like Excel files and stuff. generally we'll kind of transition to just using Stata files, which I'm gonna show you here in just a second. But yeah, if you use that XLS, it won't be able to open a CSV file. And I think the election data one, I purposely actually added that because I wanted to make that comment, so you already beat me to the punch, right? But we have to import those different types of files a little bit, make sure we're selecting the correct one, okay? Did that work for you?
Yeah.
Got sidetracks. Oh, so I changed the names here. One thing I can also do, and here, this is where, I have like an old kind of file path. Now that I have that global defined, I'm gonna kind of save this. So here, I started out with this original kind of data, and I'm actually gonna just call this new so I can show you that you can kind of create a new file. But actually, no, I don't. I'm gonna do the replace command. So let's say I try to do this, right? So I've changed the data. I can go up here to File, Save, and then I can save this as a .dta file. That's going to be not a CSV. That's going to be an actual file that Stata can open. I don't have to import it. So I'm going to call this, I don't know, state attacks, not .csv, but .dta. Save it. Now if I go to, it's still thinking, hold on. Why this computer is so slow? Save the weak material. Oh, I accidentally saved it to my other section, right? So now it's saved there, right? So you can save this file, it's now a .dta, so now notice, I had that exact same code right here. But if I try to save it again, it should get mad at me, right? Because it already exists. If I ever want to write over this, like I want the, like, let's say I wanted to rename it instead, I'm like, oh, actually I want to make sure not just state, but state abbreviation, right? Or something like that. And I want to resave it. I need to add in this comma replace command. So now, so I can go through this whole thing. Hopefully it doesn't take quite as long this time. But now it kind of writes over the old file. But I have to put in that comma replace, otherwise it gives me that red text and gets mad. Okay. Now that I have this .dta file, if I'm on the actual program, I can go to File. It's at the top, Open. And then need to be in the right section, right? They save it to, yeah. So now I say, okay, look, here's that file I just saved. Now I can just open this instead of importing it. I can just open it up and the data's right there, right? So a lot of the times what I'll do, like best practice, you don't want to always start importing these files. You want to like import them and then save them immediately as a Stata file, right? So you can just open it up instead right away, okay? So once we have this open, we can start doing some other things. So notice here, I already have that global defined. So even if I didn't already have this opened up, in fact, I can show you another kind of thing here. Let's say I didn't put this command in, right? So notice when I open that open that file, it just is use whatever the file path is, okay? That's the code. Now the interface, when I went to file open, just does that automatically for me. So I'm gonna run that code, same thing. I've already got my global defined, so it's gonna put that in for me. And it'll kind of open up that file. Right? Now, it should have yelled at me. Because if I have a data set already open, I think it's probably because I'm trying to open the same data set. Yeah, that's why. It should get mad at me. And you might have to put in this comma clear. So that clears out the old data so that I can open up the new one. I think here I don't need it because I'm trying to open up the exact same file. But if I am opening up different files, I need to make sure I put that comma clear command in there as well. Right? So I've got this state secret text data. I'm going to show you a couple other things we can do. I swear we'll eventually get to how we get some statistics from this, right? Where are we at on time? Oh, good. So one thing that you might want to do is maybe I have this entire data set, but it goes like 1970 all the way to 2019. Maybe I only want to be focused on 1 year, right? So I can use this keep command, right? And it only keeps the data where this expression is true. So if the variable of year is equal to 2000, then it's going to keep the data. It's going to get rid of everything else, right? We won't often use this command, but I'm just kind of introducing you to the program. So I can use this keep command. And now notice my data set, and sorry, I should prove to you, it ran that keep command. And now the only observations I have are from the year 2000. Okay. Another thing to point out at this point, you'll see all this green stuff, right? This is really my way to communicate to you what I'm doing in this code, so that if you go back and look at it, you don't have to remember exactly what I'm saying right now. If you ever want to make comments in your do file, if you put these double backslash in front of whatever you do, notice all that green stuff, it isn't code, so it just ignores it. So for instance, if I want to run like large sections, so let's say I just highlight all of this, it will not have an issue getting through, it'll put those comments up there, but it doesn't like, it knows that it's not code, it doesn't have to do anything, it's just displaying that text. And it's really just a way for you to like remind yourself, even as you're working on it, like what you were doing on each line of code. Here, I'm kind of telling you what I'm doing on each line of code by using kind of these comments, okay? Does that make sense? Is that clear? Okay. You good with this? Any questions up to this point? I want to just keep going if we're getting stuck. Yeah.
You might have said this, but how do you undo, like, if you just only did the year 2000 and want to get back to the full?
Yeah, so let's say I'm like, oh, I just dropped all that data, I didn't want to do that. I can go right back, just run that command where I open up the data set, and I haven't changed the data yet. The only way the actual data set changes, it's like this way. So I open up the original data set, I can then manipulate it, and the data set that I'm seeing in Stata is changing, but I haven't saved it, right? As soon as I save it, then all bets are off. I have to go all the way back to the original CSV file, kind of save it as a DTA file. So you don't want to often, like you want to just have the original data, you want to open it, you don't want to save it a lot. Like you don't, because you can always rerun the code, right? But if you like write over the old existing data, you can't get it back, right? So open the data, quite often you don't want to save it. And in this instance, like, so yeah, maybe I didn't want the year 2000, maybe I actually wanted, 2010. Now I can kind of go through, highlight these. It runs the code. Now I've just got observations from the year 2010. Okay. I can also, I don't think I have it in here. Maybe let's say I want to look at all years. Actually, let's say, maybe I don't want like any observations from the 70s for whatever reason. There was some cigarette laws that screw up whatever question I'm trying to analyze about cigarette taxes and usage, right? So instead of this keep command, one nice easy way I can get rid of this is say, okay, look, just put double backslash. I don't want to run that code anymore. Like I don't want to just keep 1 year. I want every year from 1980 and on. I can also use the drop command. So I can open the original data again, run this drop command, and now it gets rid of all the observations that were before 1980, right? So kind of two ways of like getting rid of some of the observations if you don't need them for your particular question. Okay. Any questions on that? Okay. So this is going to be kind of a cheating way of calculating statistics. I shouldn't say cheating. It's a really easy way to get these statistics, but it won't store them as like variables or anything. So for instance, here, if I use this sum command, now you can find this, and I don't use the interface often, so I think it's up here. Yeah, so statistics, summaries and descriptive, summary statistics. And I say, I forget what variable I had now. State tax. Oh. So I do a drop down. It gives me, okay, what variable do you want a summary of? state tax, standard display, I'm gonna hit OK. It'll give me the mean, the standard deviation, the minimum and the maximum, all like that. Now, it's not storing them anywhere, it's just, well, technically, it is actually storing them somewhere, but for the sake of what we're gonna be doing, we don't have to worry about that. It's really just displaying these to you, right? So you can get these summary statistics without having to make these, calculations by hand, just like Excel helped us. Stata does all that work for us behind the scenes. So it's what we call a lot of black boxing. We just tell it to summarize. I might have no clue how to calculate a mean, but if I can do that, I can get the mean directly from Stata pretty quickly and for very large data sets, right? Sometimes data sets that in fact would actually be too large for like a program like Excel to handle. I also have, and once again, if I didn't know the names, I could then like highlight this, copy it, and if I didn't already have this in here, you just paste it. Notice here there are some shorthand things for some of the stuff that Excel does, so like summarize and sum do the exact same thing. In fact, I'll talk about one here in a second that you can also use an abbreviated name for. But if you're using it more from the interface, it doesn't matter. I don't care if you put the sum or full summarize in here, it's giving you the same thing. I'll save this and post this. I can think about that, but since I'm mentioning in class, I'll get that added to the file as well. So I might want more than the mean, the standard deviation. Maybe I want things like the variance, kurtosis, skewness measures, right? If I do the same command, sum or summarize, that same variable would put comma detail. And in fact, I think here, let's do it from here. I think it's this, we'll see. Yeah, so if I select additional statistics, notice here it gives me not only the variance, the skewness, the kurtosis, it even breaks it down into my percentiles as well. So you can get a lot of information about a variable very quickly using this command, okay? Any questions on that before we keep moving? So the next thing I want to go through is this section here. So I think I showed you last class. I know I did. All right, we could create new variables, right? And we said the command that we used to do that was gen, so just generate. And I think here we added what? Tax per pack and state tax. So we said, let's create a new variable, total tax, which was tax per pack plus state tax. So this gen is a shorthand for generate. So if you ever want to create a new variable, you can use the generate or gen command, and it'll create this additional variable in our data set, right? We went through that last class. But I typically, to save myself typing, just use gen. But you can use generate as well and do the same thing, kind of like with summarize and sum. So EGen is slightly different, right? So if I just want to create variables that are like mathematically functions of or formulas of the existing variables, I can just use the gen command. Right? In fact, I can use that gen command to do a lot of different things. Like even if I just wanted to call this variable, and then I can just set it to be equal to 5 for every single person. So I can do all kinds of weird, create all kinds of variables like that. But if I want to create variables where I store statistics in there, right? Then I actually am going to have to use the eGenerate or the eGen command. So if I use the eGen command, I then can still create variables. So I want to create the first one, which is the state tax mean. So I just called it, the new variable name is state tax mean. And when I put eGen in there, Stata has all these like almost like code behind the scenes, like stored. And so when you say eGen, it can access those. I'm also maybe like not the IT side of this, explain this technically correct, but this is the way I think about it, and I think it's maybe easier to think about it. So it now knows, okay, I can pull from this group of functions, and if you just tell me mean, I know what function to do. And if you tell me mean, I know that I need to go to this data set, add up every single observation's value for that variable, and then divide by the total number of observations, right? So here I put eGen, I want to create this new variable, which is the state tax mean, and I just want to take the mean of the state tax variable. So if I do it that way, I now have the mean for every, the mean's gonna be the same for every, it's the mean, so for every observation, it just puts in that same value. Now, why are we doing this? I'll show you here in a second, and it's kind of jump the gun about something we're gonna talk about later, but I think since we're in state analysis, I'll just mention to you, and we'll talk more about the usefulness of it later on. So I can also then calculate things like the median, like that's, EGen has that median stored, so I could do that as well, right? I don't know why I would want to do that, but I can, right? So I can access all these different statistics. For me, I often don't like to use that summarize command just because it's not storing those values. Like if I start running more code, notice I have to scroll all the way back up to see what they are. If I create them as new variables, I can always just pull up my data set and see them right there. Right? So it's just a more practical kind of thing for me. It's like I said, if I asked you for what the mean was, you could use either method, but in practice, as we kind of go through the semester, I think you'll probably start to rely more on creating these variables if you want to find the mean and mean. You can also find the standard deviation. It's a little bit weird. It's just SD, right? So this is kind of a shorthand for it. So we'll hit that. Now we've got the standard deviation as well. So another reason why making these separate variables could be useful is, if I have it down here, okay. I'm doing this a little bit out of order, so we're going to skip down here because I do think this is worthwhile. So let's say I want to do the same thing, but for the PAX per capita, right? So I want to calculate the mean and the standard deviation. So I've got those commands down here. I'm going to run those. So I now have the mean and the standard deviation for PAX per capita, or what do I call it? PPC. Right? Have you ever heard, or did you talk about in 370 standardizing variables? Right? You probably did, but they might not use that terminology. When you subtract the mean from something and then divide it by the standard deviation, what did that give you? You had a normal distribution, right? And you subtract the mean, or standard normal distribution. Sorry, normal distribution. You subtract the mean, divide by the standard deviation. That gave you a standard normal distribution. Right? You were standardizing the data so that you could then use those standard normal tables or Z tables, whatever they called them, to figure out the probability of seeing above or below this many standard deviations above or below the mean. Right? So when I'm looking at PAX per capita, I might not necessarily be as interested in what the actual number is for these specific, I think they're states, but I might be interested more in, well, how unlike the other state, how much unlike the other states is this state? How far away is it from the mean of other states? How many standard deviations away is it? So I can standardize a variable by taking that variable, subtracting the mean, which I have calculated, right, for every single observation here, divide by the standard deviation, which I have in a separate variable here as well, and then create this new variable, which is PAX per capita, and I put stand for standardized, right? You can call it whatever you want. So now when I run this code, it's now taken these PAX per capita numbers, which I don't know if 139 is a lot, 89, and I can now say, okay, for this state in this year, it was 1.32 standard deviations away from the mean, and this state was 0.82 standard deviations away from the mean. In fact, are there any negative? There should be negative ones. It's impossible for them not to be. Oh, here they are. It's probably because then later people, I know why, because people smoked a lot more in the 80s than they did in the 2000s. So you start to see when we get to later time periods, well, now they start to be below, right? There's a certain number of standard deviations below the mean. I thought that was weird, but I wasn't thinking through the actual variables here. So it's going to be useful for us kind of down the road just to know how to standardize these variables. So it's something I bring up here just because I'm also talking about creating these mean standard deviation variables. Okay. Any questions over this? And kind of, I also put in a note here just to kind of emphasize, if you're creating your own variable, that's where you go back to just using that gen command. That EGen is just when you're trying to call these built-in functions like mean, standard deviation, or SD, etc. Okay. Any other questions before we keep moving here? Okay. One more thing. So I showed you scatter plots. You can go up here to Let's see if I can remember what's that. Statistics. Should have looked this up. Here we are. So summary and descriptive statistics, that's where we're getting the summary stats before. But you go down here to no, that one. Why am I not seeing it? Probably looking right through it. No, it doesn't matter. But you can do correlations and covariances. So maybe I want to find the covariance between tax per capita and total tax, right? Hit OK. They'll kind of give me this matrix that, you know, how is tax per capita and tax per capita correlated? 1 to 1, right? Perfectly, they're the exact same value. What about total tax? 1. But that other value, kind of matrix where total tax is tax per capita, that's telling me the covariance, right, between, sorry, this is not the covariance, this is the correlation coefficient. It's already kind of divided by the standard deviations. It does all of it behind the scenes. It calculates the covariance and then divides by the standard deviations of these two variables, and it gives us this correlation coefficient between the two of what, like -0.7. Okay? So really quick, easy way, you don't have to calculate by hand, to get that correlation coefficient pretty quickly. I know there's a way on the interface to get to it. I forget what it is or exactly where it is, but you'll have the code, so that should be more than enough. It's somewhere under, oh, it's because I was on, it's okay, never mind, I know where it's at. Statistics, two-way graph, and then you can select what you want to be on the X and Y axis. So let's say on the X axis, we want to put, I want my scatter plot. On my X axis, I'm going to put total tax, Y axis, tax per capita, hit accept, hit OK. This might be slightly different than the example here, but that's okay. So it gives me this nice scatter plot, right? And I can kind of quickly see, like, even if I don't have the correlation or covariance, I can see that there's kind of this negative relationship between tax and usage, right? And in fact, initially, there's a pretty quick drop off. Once I get to a certain point, it doesn't really have much of an effect. And this makes sense economically, right? Initially, when I start increasing the tax, people who like smoke but like aren't like really addicted to it probably stop smoking as much. But at a certain point, the tax gets, you know, all those people stop smoking. Who's still smoking? People who are very, very inelastic. You can keep on taxing them, and they're going to keep you smoking the same amount of cigarettes, right? So we can kind of see cool stuff like that just from a scatter plot, pretty basic. I think I did this one. I did different variables here, or not, sorry, cost per pack and state tax. Obviously, this one we're going to think is probably more 1 to 1, right? As the state tax goes up, the cost per pack is probably going to go up. So I'm going to run that one. It's the same code. So once again, once I run this once, I know the format that I need to create a scatter plot. I can just copy and paste this into my do file. And then if I want, I can, so copy and paste it into my do file. And then if I want, I can start to do scatter plots of different variables, right? So sure enough, right, the cost per pack should be, part of the cost is the tax. So this makes sense. That's almost like a direct linear relationship here, okay? Any questions on any of that? So I think that's all we'll probably do today, unless we have a little bit more time. Because this will all be week 2 stuff. So I will probably drag and drop this review of statistics do file when I create the module 2 on Canvas. I'll probably drag it down to there since we'll be using it next week as well. But just know it has stuff that we did in this week 1. A little bit weird this first week. So I want to go back to slides here. Talk about conditional distributions. Okay. So kind of talking about distributions, we mentioned some skewness stuff. We also can think about distributions are going to differ if we start to put limiting factors on or conditions. Right? So I'll give you an example. So if I want to know what's the average, let me think of a good example. So if I have an unconditional mean, Like, let's say I'm interested in the average number of beers consumed by a US citizen, right? I don't know what it is, probably not super high, whatever. But what if I say I want to know what's the average number of beers that a US citizen consumes given, so this conditional, this vertical line is given that this other thing is true, what's the expected value of the mean number of beers drank? Conditional on the person is a college student. It's probably a lot higher than the national average, right? And so when I start putting these conditions, I might get very different means or very different expected values. So you can kind of think of it almost like group means when we're putting on these conditions. I can look at the mean of different groups, right? I'm conditioning, I'm only calculating the mean for the observations where this is true, right? So I could even do, I could just use age. What's the average of this variable if X is equal to, or the age is equal to 18, or if it's equal to 19. I could get a distribution for every single year of age, or a mean for every single year of age. I think I did like math scores on different tests and parental years of education. So I had this like I-step data. How many of you went to Indiana school, like middle school? Couple. Did you guys take the I-step? You know what I'm talking about? It's a standardized test. I've got some data. I don't think you'd be in it because I think you guys are getting a little bit too young to be in the data set. But you can ask for it from the state. You can't get the names, but you can get all the I-step data. So if I'm thinking about math scores, right, given the student's parents' years of education, I might expect that if their parents have a higher level of education, those students might be doing better, right? Those parents might be having their students a little bit more prepared to go to school, might be helping them more with their homework, et cetera. So I think if I look at the actual data, sure enough, when and then it's 0.00, there were some other decimals, but we're going to round to the second. For those who only had a high school degree, 12 years of education, the math scores were a little bit lower than for those students whose parents had a little bit higher education. So we can start to tease these things out of the data, and we'll go through this next week. I'll show you how we kind of calculate means, adding in some conditional statements in Stata, right? So, but this idea of conditional distributions, the distribution might look differently once we condition on something. And then I did what? Yeah, the value of a college degree, or your parents getting a college degree. You can take the difference, and that's what, 4? So yeah, so you get a college degree, you can expect your kids to do about 4 points higher on some standardized tests. I don't know what that means to you, but right, just an additional benefit, right? You're going to see that you do the same thing with salary, right? Instead of your kid's math score, you could say, what's the? And in fact, I used an article in my B251 earlier today. The Federal Reserve of St. Louis, I think, put out, but they did this like comprehensive study, and they were looking at like average weekly earnings of a college degree versus only a high school degree. If I remember right, it was like 1,200 versus 800. So it was like a pretty whatever it worked out to be, it was like a 68% increase in expected salary over your lifetime if you get a college degree. So good on all of you for being here, right? Now, when we're talking about these conditional distributions, we can also have independent events. So this is things like, maybe I want to know what's the expected math score of someone who is, let's use something not correlated. Let's say, what's the average math score of the student given that they're 4'9"? Well, the height of the student probably shouldn't tell me really anything about their math. Maybe there's a story you could tell about, if you're shorter, maybe you're more likely to get picked on, and maybe you're shyer. So, but for the most part, that should be something that's completely independent of your intellectual ability, right? So sometimes if we condition on something and we get the exact same value as the mean, that's telling us that whatever we conditioned on has no relationship, is completely independent of that variable y. And we'll start to rely on, and we'll need this independence for certain things that we talk about throughout the semester. So you only have an independent event if the mean after you condition on this thing is the same as the overall mean. I don't know, that example is not, it's whatever. So if you did have independent events, when you look at the covariance or the correlation coefficient, it should be 0. Or, it's often we never get something that's truly 0, something very, very, very close to 0, 0.001 or something like that. I don't know, I can draw this out for you. I think you probably get the gist of this, but we're thinking about what this looks like visually. you know, we might see something that looks like this, right? And then we condition on, you know, whatever this variable X we're interested in, we have this additional condition. We're still looking at X, but it's now conditioned on Y being equal to, I don't know, some value. Well, now maybe that shifts our distribution. Maybe it doesn't shift it. Maybe the mean's still the same, but maybe we get, so the means could be the same, but maybe if we condition on this thing, maybe we get like a skewed distribution, right? So the mean might end up being exactly the same, but it's got a different kind of symmetrical properties to it. So it can change the mean. It can also change what the whole distribution looks like when we're conditioning on something else. And I think that, like I said, intuitively kind of makes sense, right? We're looking at very different groups. Right? All right, so where do I want to? Got 10 more minutes. Let me see what else I have to get through because I know we're not going to get to sampling. It's probably be safer. I think we got enough time to at least introduce this normal distribution, and this will set us up pretty well for next week. Okay. So I mentioned this a little bit already. When we're standardizing these variables, it's kind of connected to some things you probably learned about, like creating z-scores. Right? So the normal distribution, right, has these really nice properties where it's perfectly symmetric. So the mean is the same as the median, is the same as the mode. We can define it, right? Just because we have a normal distribution, they're not all exactly the same. They can shift if they have different means, and I've already alluded to that today, right? So here I've got 3 normal distributions, but if they have higher means, it's just going to shift them along the x-axis, right? They're also defined by the variance or the standard deviation. So here's maybe a normal distribution that has a variance of 5. What happens if the variance gets higher? What's going to happen to the shape of this distribution? Yeah, it kind of works in opposite directions. As the variance gets higher, my distribution gets flatter and flatter. Why? Because the variance is telling me that there's more deviation from the mean, or that I'm going to have a lot more observations out here in my tails. Okay. So as we get kind of this higher and higher variance or higher and higher standard deviation, I'm getting a flatter. They're still normal. They're still symmetric, right? But it's getting flatter. Okay. I had some data laying around. This is another thing you can kind of do in Stata that create these little graphs. I had men and women. This is also true, I believe. So it's true about a lot of things with men, and I know there's a physical reason, biological reason why, and I can't remember what it is. But even though men are taller on average, right? What's also true about male height, based off of this visual? Bigger variance, right? So a lot of the times, like I said, I know there's a biological reason as to why, but a lot of times when you look at different physical metrics of men versus women, there's going to be a difference in the mean, but there's also quite often a lot more variation in the male data. Right? Once again, that's not my expertise, but I do know, like, I have data sets and I see it all the time, so I know this. So one thing we talked about with this normal distribution, a property that will come out of it, and we'll kind of hit this more next week, and I'll pull up in the Z tables and I'll kind of go back through those, is if we were to go one standard deviation to the left and the right of the mean, there will always be, if it's a normal distribution, there will always be what, 68.3% of the data within that range. So if you can calculate the mean and the standard deviation. We already saw how we could do that with a data set. If I were then to go one standard deviation above and below, 68% of my data will be in there. Okay. If I go 2 standard deviations out, right? That's pretty far. Just going 2 standard deviations, I'm getting 95% of the data. 3 standard deviations, 99.7%. So, most of your econ majors, do you know any Kelly students though? So, yeah, so have you ever heard of 6 Sigma? Something like with companies and businesses, it's that they want to be so precise with things that they take things out to 6 Sigma, right? So 3 Sigma is already giving us 99.7%. 6 Sigma would give you basically 100, right? You're almost guaranteeing that there's going to be nothing that's outside of your range, right? From this normal distribution, I'm talking about things like how many standard deviations away. Well, I can figure out what those values are once I calculate them, and I standardize those variables, right? We took earlier, packs per capita, and we standardized it, right? So I knew how many standard deviations away those observations were. I can do the same thing here. I can standardize any normal distribution by taking all of the data, subtracting the mean, dividing by the standard deviation, and that would give me this kind of nice standard normal distribution that will not only have a mean of 0, but it's always going to have a variance of 1. Right? And you can probably Google, if you wanted to, mathematical proof of mean and variance of a standard normal distribution. It's not overly interesting, but you can kind of prove if you subtract the mean from every single data point and you divide by the standard deviation, you will always get, from a normal distribution, you will always get a standard normal distribution with mean 0, variance 1. Okay? And like I said, this should kind of be review, just to kind of put a visual to it. Like we can go, once we have these z-values, we can start to think about things that are 2 standard deviations below the mean, 1 standard deviation above. A z-value of 0 would be what? An observation that is exactly equal to the mean. Yeah. All right, so this is how we can kind of think about these z-scores. And then we can look them up in the table and say, okay, what's the probability if I selected an observation at random? What's the probability I see something, see a value 2 standard deviations below the mean, or something even further away, right? Or what's the probability I see something within 1 standard deviation above and below? That's where all these values were coming from that standard normal table. This actually has a function to it. We can integrate it. Don't worry, we're not going to be doing integration by hand, right? We're going to rely on Stata to do it for us. Okay. Is there anything else I want to say here? We got z-scores. We talked about standardizing variables. It's essentially what we did in Stata earlier. We just take the value of x for whatever variable we're looking at. For every observation, we would subtract the mean, divide by the standard deviation. This gives us these nice new z-scores, which represent the number of standard deviations the way that data point was from the mean. Right? And that's how we can interpret them. A z-score of 3.5, 3.5 standard deviations above the mean. Z-score of negative 0.2, 0.2 standard deviations below the mean. So we got a little bit early. I'll kind of end it here. Before I do, are there any other questions for me before we kind of keep moving? Okay, so that first quiz won't be until after next week. So I kind of mentioned we're gonna have like 3 before the midterm, 3 after. So it will cover some of this material. So I'm gonna get some prepping. Before I say this, it might actually be up there. I don't have it up there yet. I'll throw up some kind of practice problems like over this week's material, just like kind of what we talked about today. You can kind of start thinking about what will help for that quiz. It also contains stuff that we do next week. So obviously that we haven't covered yet, but I'll get that put up there, and I'll probably start putting up this afternoon some week 2 materials as well. So you'll start to see those pop up. Okay. So one thing I would highly suggest before Tuesday, make sure you can get Stata working on your computer. If not, reach out to me. I can try to, actually what might be helpful if you can't, even Zoom meeting where I can kind of you can screen share and walk me through exactly what's happening. Other than that, any questions for me before you go? Yeah.
How often do you upload videos?
Yeah, so they should. It's a good question. I have a class right after this, so it won't be immediately after class, but likely when I get back to my office in the afternoon. So I think now you've got me second guessing myself, but I believe this section is the bigger one. So here's Tuesday's recording. Here's that kind of starting Stata alternative. In that recording, I actually have like the way I showed you guys how to do it. I guess you get it in class. But if you do need any help with that, like you said, you can find a point of lecture where I cover it the first time. And then if you're having an additional thing where it's giving you kind of that error that it's not opening up Stata files for whatever reason, you have to go to that settings tab and activate it. Other than that, hopefully semester off to a good start, fun, safe weekend. I'll see you guys on Tuesday.